Robert Richardson on the dash.
Okay, so good morning everybody. It's a great pleasure to be here today. So yeah, my talk today is going to be about exploration robots. That is, robots to go and find interesting things in unusual locations. You've heard already a bit about myself, so I won't spend too much time on this. My background is very much in robotics and mechatronics. So robotics being autonomous systems, mechatronics being electronic, mechanical, computer science to do things, maybe things like smart cars, that kind of thing. So at the University of Leeds, I've been there for a long time, University of Manchester for a bit, and now I'm a full professor in robotics at the University of Leeds. I run several projects, I won't go through them all here, different areas. Most of my projects are around physically creating robots, but also things in the area of smart cities for robots, which you heard about a few minutes ago, and also sampling material with robots. So I'm from Leeds. I guess some of you don't know where Leeds is. So Leeds is in the UK, of course, the northern part of the UK. It's over here somewhere, not so far from Manchester. So if you are in the UK, please do come across and see us. Very, very much welcome. It's been an interesting kind of shock coming here. So about a week ago or so in Leeds, we had snow, so we were in thick snow. So it's quite a change to come here and feel the beautiful heat, which is fantastic. So today, of course, I'm focusing on exploration robotics, but Leeds does many things apart from that. So we have very strong themes in therapy. Therapy is things where you can use a robot to recover your lost strength. So if you imagine rehabilitation, you've got a weak arm, you then put a robot on yourself, and it helps you to recover that lost function. So a lot of work in that area. Also on assistive and enhansive robots. Now these are robots you use when you've lost a function and you can't actually do things. So for example, you've lost a leg, you've lost an arm, you need a prosthetic device. We do robots that can help you to maintain a standard of living going forward. Also surgical technologies, so robots to do surgery inside your body, a lot of work in that area. And of course, lots of fundamental work in AI and that kind of thing. But today, of course, is about exploration robotics. So by this, we're talking about putting robots into places mostly where you wouldn't want to go yourself. So they could be dangerous, they could be small, they could be different kind of environments. And of course, these environments exist across all domains. So we have some in, obviously space is an obvious thing. I won't talk about space much today, or talk today, but space is obviously a good example, quite a specific example of exploration robots. Also deep sea underwater, again, I won't talk much about this today, but deep sea underwater is also very important. I'll be talking most today about things actually on the land and in the air. It'll be a bit loud maybe. Yeah, mostly on the land and in the air. So how can we do exploration robots in that kind of environment? So people say to me, well, you do exploration robots, that's great, building all these amazing toys. Is it really useful though? You know, all about business case. Show me the money. Why would we want to do exploration robots? But in fact, exploration robots can impact across many domains. So for example, of course, things like agri-food. You want to go out to a field, you want to find some crops that are damaged. That's kind of exploration. Healthcare, you want a robot to go inside your body, find a tumour, that kind of thing. Obviously nuclear decommissioning, going in there, finding things that are damaged. Security is quite obvious. So really, although it's kind of fun, yeah, we're going and sending robots to interesting places, it has a really strong business case, and it is very worthwhile doing so. That's why I defend what we're doing. So I always like to start the presentations at the end, which is always good to do. So I've got a very short clip I'm going to show you of the things we've been doing in the last year. Yeah, so lots of fun there had there. So yeah, I'll spend a few minutes, of course, as we go through talking more about these things. But it gives you an idea of what we're doing. So physical robots that are out there doing things, exploring and getting data. So before I go into the detail of what I've been doing, I want to just take a few moments just to kind of briefly bring up to speed. I guess some of you don't know at all about robots. So I'll just briefly mention about a few things about robotic systems so you get a flavour of what's going on. So a robot, of course, is a physical system that moves. So a robot is defined differently from, say, the internet. The internet's not a robot. It must have the ability to go somewhere and by itself. That's one of the definitions of it. Ideally, it's autonomous. We'll come into in a minute. That means it can do its own kind of things. But a robot, so you have a robot, physical system. It will have a battery, of course. It would have sensors. And it can move and it undertake operation. This robot here actually has been designed by one of our third-year students as part of their project, so it's really nice. I'll put it on here. It's a good example of the kind of things we're doing. In fact, it's so good I may actually build it. It's quite a nice robot. So it's part of a student module to design them, but I like it so much, maybe I'll go and build it. But yeah, so when you're designing robots, ideally you have a nice linear structure. So someone comes to you and says, I've got this amazing thing, go and build a robot to explore, for example, a pyramid, something like that. Ideally, you have the idea, you go straight down, design it, build it, and it all works. Of course, as many of you know, I guess, it never works that way. You end up with kind of a crazy spaghetti thing going on here. So you have a problem, you try and create a robot, but then you find, you test it, it doesn't work. So almost the curse of robotics is this cycle of testing, refining, trying to improve it going forward. When you're making robots, you probably mostly think about making robots in quite a large scale up here. So there is conventional manufacturing, which is kind of cutting metal. It's quite up here, quite big. But these days, you can make things with many, many different techniques. So you have very small things you can do, chemical etching. So we're building robots now right down to things you can't even see. So incredibly small robots. So there's a whole scale of things. And when you're designing a robot, of course, how you physically make it is very important. So you'll be thinking about the manufacturing scale on that. Of course, it needs to move. So to make a robot move, you need different kinds of motors. You have things like a brush DC motor, a brushless motor, and a stepper motor, for example. So a brush motor, what that means is you have magnets in here. You apply electrical current. When you apply electric current, of course, you get things to oppose, they spin. And it's called a brushed motor because the connections between the electricity and this thing that spins is in contact like a brush, and that means it can then maintain contact and also change direction as it goes forward. So simple, cheap solution, but these brushes do cause problems. We'll come on to, I guess, later on, but they do cause problems on that. A different way of doing it is a brushless motor. Working on the same principle, you have magnets that attract and repulse. In this case, though, you're switching different coils. As you switch different coils, you can attract it in different directions. So by doing the orange, the pink, and the green in sequence, you kind of cause it to spin around. So it's simpler mechanically. There is no contact between the actual mechanical thing, so it can have less wear, for example. But it's more complex in the sense that you have to have pulses of electricity to make it spin around. Stepper motors are a more extreme case. In this case, you have two different coils and potentially hundreds or so of steps on this. So similar kind of idea, you pulse it round and it rotates. Also, it can be not just electronics, it's not just electricity, it can also be pneumatics. So for example, you can use air to control robots quite straightforwardly. But in this case here, you put air in here, this rod pushes out, and that creates mechanical work to do something. You can use gears to change the amount of force you apply, which of course is quite important, so you can change the gears, change things around. In terms of making it move, I guess you want wheels. There are different ways of configuring wheels. So if you look from the bottom of this, different examples here. So of course this one here is like that. So you have two powered wheels here. So these passive wheels are these ones here, these black ones. And these wheels here are driven. So you have different configurations. This is quite a simple way of doing it. It'd probably fall over. You can have more complicated solutions, things like tracks and so forth, to make them move in different directions. Of course, you could use legs. Legs are quite common. So, but the problem with legs are they're quite complex. You need maybe 10 or so moving joints. Complexity adds time to manufacture, it adds risk of things going wrong, it adds cost. So the reason we don't see lots of leg robots walking around, we could build them now. We don't see them mostly because they're expensive. If it works with 2 wheels, why would you want to put on legs? But they are nice and they have really good quality in specific application areas. And of course we also have humanoid robots. So again, why don't we see lots of humanoid robots walking around? It just comes down mostly, there are some still technical barriers, but mostly it comes down to actually the complexity and the cost. This one here, for example, simplified, it has 47 degrees of freedom. That is 47 different ways, different joints. So to make a walking robot, 47 compared to a wheeled robot with 2 motors. So a massive difference. And of course, robotics is about productivity. It's about doing things the right way. So you have to have a good reason why you'd want to build a humanoid robot. Batteries are very important. In fact, one of the biggest developments in the last few years is battery power for robots. Lithium and polymer batteries make a massive difference. This is often driven by the car industry. So people making autonomous cars, electric cars, are investing huge amounts of money into better batteries. And this better battery power is helping us on our phones, but also for robots. And it's going to get better and better. Once we get beyond a certain point with robots, that can run for a week, for example, we're going to see much more use of these things in the world. Of course, sensors, you need to be able to detect what's going on, sense what's going on. There are all kinds of sensors out there, detecting gas, detecting leaks, this kind of thing. You have sensors that can measure the internal joints. Of course, that's important as well. So you need to measure what's outside the robot, but you also need to measure what's inside the robot. So how do you measure things? So as a person, you have measurements from your muscle fibers, you know where your arms are. In the same principle, a robot needs to understand where it is, where its arms are, so you can have angle measurements inside the joints. In terms of external sensing, you want to, of course, perceive the environment. You have these things called sonar sensors. These work by sending out pulses of sound and then measuring the time they come back. They're great, they're cheap, they're very, very cheap, which is good. They have problems though. So for example here, this is a perfect room being scanned by a laser scanner being a very precise laser beam, gives you very crisp things. If you try to do the same mapping with a sonar sensor, you end up with this kind of weird effect. These are caused by reflection. So you send a pulse of sound out, you want to measure it coming back, but what happens is you measure the first one coming back, it then bounces around and you measure it from somewhere else. So you end up with weird problems here that can be quite hard to overcome. So there are different ways, but the important thing is you can perceive the environment. Of course, vision using images from a camera is very important, and it's making massive progress. But even now, still, we struggle to understand a scene. So if I give a photograph of an apple, it's pretty sure that I can get a bit of software to say that's an apple. Google do it all the time on their servers. What's still really hard, though, is if I was to photograph this room to try and work out that's a window, these are people, that's a chair, that person's wearing a watch, really hard to get that kind of level of what we call semantic vision. So not just here's a photograph, but understanding the meaning of what the things are in the scene. So for example here, here's a room. Ideally you want to do some semantic vision to understand where these things are. This is a wall, that's a door. This is quite a simple example here. Even that's quite hard to do, so it's quite a big challenge. In terms of autonomy, so the robot itself should go and do a task in a certain way. The industrial approach to this is what they call the sense, think, act cycle. So the robot sits there, takes a measurement, what do I do? Executes that measurement, and then senses again. So it's a kind of a sequential process of measurement, action, and measurement again. And that works fine in a very restricted industrial environment. When you're in a more complex world, you can't focus on one task. You need to be more open. So rather than this kind of sequential thing where you measure, you do stuff, you actuate, and you do it again, there are other things which are kind of behavior-based approaches. These are mostly done on things like robot vacuum cleaners, other things. In this case, you have many possible things you could do. So for example, you could wander around, you could avoid something, you could give someone a cup of tea, many, many choices, and these choices are activated depending upon what you sense. So it's not a single operation, many things on here. Some things have higher priority, some things are more important, don't fall down the stairs, very high priority. Other things are less priority, but by doing this kind of approach, it gives it more flexibility. The problem with doing this is you don't have a guaranteed action. So in the first case, you could absolutely guarantee it'll measure this, it'll do this. In this case here, it's sensing things very hard to predict exactly what it's sensing and exactly what it will do. And that's a problem in safety critical applications like autonomous cars, for example. How do you guarantee what it will do in specific situations? It's quite difficult. In terms of autonomy, we have levels of autonomy. So if you're controlling a radio-controlled car, that would be autonomy right down here, autonomy level 1, no assistance. The person is fully in control of what's happening. But you can gradually increase that. So number 2, for example, is you're radio controlling your car, but at the same time a computer is saying to you, do you want to turn left? Maybe you want to go right. So it's giving you advice, but you're still fully in control of the car, but it's suggesting actions for you to decide what to do. As you go up the autonomy scale, you end up with things like, for example, number 5 now is where the actual computer will try and do something, but ask your permission. So it will suggest an action, and you say, yeah, that's good. So all you're doing now is saying yes. A big red button that says yes. You press the button, yes, yes, yes. And this gets more and more advanced until really, at level 10, I think level 10 we never want. Level 10 is far too much. At level 10, the computer does whatever it wants, whatever it decides, and will never, ever listen to a human. That, of course, is really extreme situation. So I can never imagine with one level 10. Level 10 is kind of a separate autonomous system. But certainly level 8 is quite a good, so it's doing its own thing, mostly by itself, but you can control it if you want to. There are also different principles. So we talk about autonomy. There are important things around what a robot should and shouldn't do and how it should operate. So I've given you one here. One is, I guess, quite obvious. A robot should not go away and kill somebody. Hopefully it's quite obvious. That's not a good thing to do. I'm interested if anyone's got any suggestions of other things. I'm going to show you a set of guidelines from the UK in a second, but maybe we can just have maybe 2 examples of what a robot should or shouldn't do ethically. I'm going to put you on the spot now. Anyone got any thoughts about what would be a good thing to do for a robot? I'm going to pick up some of the lights. Give me an example. So what do you think? So what would be good? So it shouldn't kill someone. What else should a robot do? Any thoughts? Any volunteers? Wake up. No volunteers at all. So if you can kill somebody, how about a robot that shouldn't damage your property? Would that be a sensible thing to have? How about a robot that should not kill itself? That would be quite good. So I'm going to get one volunteer. Volunteers? Okay, I'll let you this one then. I shall give you the answers, not too quickly, hopefully. So, one of the important things here is that it's the humans that are responsible for what's going on. So the humans, the robots must do what the humans want them to do. You don't want robots going to do their own thing. They're always going to act on the best interest of yourself. They should be designed to, obviously, to do safety and security. I'm sure you knew these things. I'm sure you were just too comfy in your seats. I think this is quite interesting. This one here is quite interesting. That a lot of work's going to robots that are used in care homes to help people, and sometimes they're being designed to be dogs, designed to be cats, to make people feel better. But very importantly, they should not deceive. So it should be very clear what is a robot and what's not a robot. That's quite interesting. And also the last one here is quite interesting. Very importantly, legally, you've got a robot. Who owns that robot? Very important. So you can't just have a robot that nobody owns. So if a robot damages your driveway, who pays for that? Very importantly. So these are kind of important things. These are guidelines we've done in the UK, we developed to make sure we're doing ethical approval for robots. Okay, so I'm going to talk more about specific things. So I've given you a background now, a bit of a flavour of robots. Let me go into more detail about different things now. So when we explore things, we have different categories of exploration. One of them is open spaces. You want to explore somewhere that's really quite big. The challenge here is much more around endurance. How can you operate for a long period of time? And how can you store the data? Another environment is when you're working, for example, in pipes. In this case, it's very confined. You have no space. It must be built to be small, contained, and this kind of thing. So there are different environments. I'm going to talk through different examples in the context of how they operate in different spaces. So the first one is open spaces. You can see here a very large open space, autonomous robot. So we're building robots to explore this space. In particular, we wanted robots that drive in better ways. So if you imagine a car with a sensor on, as you drive around, if you want to turn direction, you have to go forward and turn direction. You can't drive sideways. So we wanted to be able to have a vehicle that can move in different ways, in different directions. So for example, what we have here, we have a triangle robot. It has these 3 sets of wheels on, and each one has 2 wheels here. And by rotating these 2 wheels around, we can make the vehicle drive forward, drive left, or even spin on the spot. And how these wheels turn direction, there is no central motor here. There is no motor here. What happens is, if you want to spin that central axis, you reverse the wheels. So this wheel goes forward, this one goes backwards, and then you can induce the actual module to spin. So these wheels cause the forward motion, but also by controlling them, you can turn them around in different directions in different ways. So I'll show you a video here. So you see what here? These wheels are spinning on their axis. They're doing that not by a central motor, by the wheels themselves spinning in different directions. And you'll see here it can drive around in different modes, it can drive around in different directions. This is a conventional kind of driving, so the front wheel's steering, and the back wheels are doing things. They're very much a conventional kind of vehicle now at the moment, which has its uses, but not great for an autonomous vehicle in a kind of confined space. Of course, you can go forward, you can go backwards as well. But now it gets more interesting now, so we can do stuff we couldn't do with a conventional vehicle. So we can cause the wheels to spin on the spot, so you've got a spinning motion. So the camera on here, of course, now is spinning in a circular arc that you couldn't do normally. And you can also, so what we're going to do here, we're going to keep the camera facing this direction, and we're going to drive around in a square. So we now can drive the vehicle around in a square configuration, whilst the sensor is always pointing in the same direction. There are things you can do with mathematics to try and cope with the camera moving, but far better to point in one direction and drive around in different directions. So you can see here, again, the camera's still going here, we're driving in different directions. So it's quite a nice example of a different kind of ground vehicle we're looking at. Of course, with this we can do much more complicated things, so we can cause the vehicle to spin. So in this case here, we've got a triangle here. We don't have to spin or drive forward. We can actually drive forward and spin at the same time. So in this case here, this is the point of the triangle here. You can see as it drives forward, it spins around. So in this case here, it's more obvious. It's driving forward. As it drives forward, the whole body will be spinning around. So you can do all kinds of complicated things that you couldn't do in a more conventional way. So that's open space on land. We've done some work on open spaces on water. The question is actually done a couple of years ago and led by our level 4 undergraduate students. So it's an example of an undergraduate student project that actually got out into the real world and made some really interesting results come forward. The question here is though, how do you actually find out how much water is on a glacial melt lake in the pool? So a melt lake being something that is frozen some of the year and other parts of the year is unfrozen. So how can you find that out? You can use a satellite camera to look from the sky and you can see the surface area, which is interesting, but the problem is the surface area doesn't give you the volume. You could assume it's kind of a cone, it's a ball, you can make assumptions, but you don't know. So we want to go onto these lakes and work out the volume of the lakes. If we can do that, we can then work out from the air, hopefully if there's a correlation, from the air from the satellites, how much water is stored on the melt lake. So it's in this area here, the Kumba area of Nepal we're working in. So building small autonomous vehicles. The key thing here is that the very large lakes in Nepal have been surveyed by people with boats rowing around and dropping sensors in. So it's a bit of a hassle, but you can drive there with a truck. It's not so bad. What we particularly wanted to do was to look into smaller lakes. The smaller lakes typically are hard to get areas, so we need to have big lakes. Obviously there are more smaller lakes in different areas. So a backpack portable vehicle you can take to there, you can leave it there, it'll autonomously survey the lake and give you data back. And here's the vehicle here, so it has 3 sections. The 3 sections unplug. We have quite big clips here. It looks quite clumsy. The key thing here is though, you're deploying it in the snow wearing thick gloves. You don't want screwdrivers, you don't want anything fiddly. Simple things, pull it out, take it apart, put it in your backpack and go home. We have a thing here as well, a winch to lower a sensor for temperature. So we can use a sonar sensor. Much like I showed you at the beginning, you send a ping of sound out, you get a reflection back. If you do that, you can work out the depth of something. But we don't know the temperature gradient. So here we have a temperature sensor on a winch, so we can stop somewhere, we can lower it down and measure the temperature profile of that lake. So you can see here it's a beautiful, beautiful area, really, really beautiful. Much colder than it is here, of course. And down here is our little boat. I'll zoom in a little bit. There we are down there. So we're trying to survey these kind of environments here, quite difficult environments, with our little boat. If you want to see what it's like to be on a melt lake, here's a video on top of the boat driving around. You can see it's quite flat. You can also see some of this test stuff here is actually falling down. So it's quite a dangerous place to be on a boat anyway. So we're floating around here, driving around. As we drive around, we're pinging down sonars to measure the depth of the bottom of the lake. And the way we do it autonomously is, you put it in the lake, you drive it around with a radio-controlled device. So you drive the perimeter of the lake. Once you've done that, you defined a boundary. Then the robot can go away autonomously and do stuff. It's trying to do a spiral search here. What it's trying to do is trying to spirally search. It's getting a bit blown around by the wind, that's okay. We've got a mostly spiral search of the lake. That gives us a contour plot like this. So we now can estimate the volume of the lake from that. And the really great result of this is, if you compare the blue dots with our red dots, you'll see